Okay, so we'll start off with the presentation. So basically a short lecture on the energy sources, their practical applications. More than going too much into theoretical aspect of it, as a laparoscopic surgeon or in laparoscopy, what is it that you need to know about the energy sources and their applications? I'll just share my screen. Can you see my screen?
Yes, sir.
Yes,
Yeah,
yes, sir.
thank you. So as I said, energy source and its practical applications. So as an overview, we'll just touch upon the various different energy sources we use in surgery, specifically laparoscopic surgery, the monopolar energy, the bipolar energy, the advanced bipolar, and the ultrasonic energy. These are the most common sources of energy we use, and we'll differentiate between them and see their practical aspects. So first, we'll just delve into the basic mechanism of it, then go into the pros and cons and also the application. Okay. So basic principle in any source of energy sources, if you want to understand in very simple terms is that even whenever somebody comes to observe, somebody asks me, it's very similar to cooking. You're basically trying to cook the tissue using the heat generated. So that heat could be generated either due to electrical resistance or directly due to the thermal energy which is generated. So what basically happens is that the tissue is not a very good conductor of electricity. So when electricity passes through the tissue, as per the laws of the physics, there is going to be intense amount of resistance which will be generated. This resistance causes heat to be generated at that side. The same principle how our filament bulb used to get lighted up because of the high resistance of the tungsten, it used to get heated up. The same principle applies here. The tissue gets heated up because of the electrical resistance, and due to that, the water in the tissue evaporates. This causes the proteins to get denatured and get coagulated, and this is what causes the coagulation or sealing of the tissue. When it comes to vessels, it's sealing. When it's normal tissue, it gets coagulated. So lesser the tissue chunk, it's easier to cook and better the sealing. These are all just very basic principles of kitchen cooking which we use. Like if it's a thin chapati or thin roti, what happens is cooking is easier. It happens very soon. But if the tissue is very thick, similar to a very thick dough which you are trying to use for a chapati, then the cooking will be very slow. The center core is not going to get cooked. So with that basic understanding, we'll just first touch upon monopolar energy source. So as the name suggests, monopolar energy is a unidirectional energy. So what do you mean by unidirectional energy? If you see that monopolar is the only energy source where you have to use a body plate, a plate which is kept under the patient. This is because the current flow happens from the monopolar machine, which is also called the ESU. ESU is the most common term, electrosurgical units. These pieces are called the electrosurgical units. So the electrical energy arises from the electrosurgical unit, goes through the cord, goes to the handpiece. From there, the tissue, then to the through the body of the patient, it goes to the plate and back to the machine. So this entire circuit has to be completed for monopolar to work. So if you see that the entry point of the electrical energy or the current, that is the handpiece you're using, be it open or a laparoscopic surgery, it is always very pinpoint. It's a small thing. That is to reduce the resistance and to ease the amount of electrical energy or the flow of electric energy. So the site where the monopolar hook or the handpiece touches is the site where energy gets transmitted and heat is generated. But if you see that exit is very broad, this is because there should not be any source of thermal energy generated at that point of time. So what basically happens in many a times is that if there is a leakage of current at the site of exit, or if there is faulty insulation, or if the proper body contact does not happen with the widespread plate and the body, like if you put it in bony prominences, or that there is no contact because of some tissue in between, or the cloth coming in between, or any cable in coming between, if the exit point is narrowed or becomes pinpoint, there is high chance of burns happening there. This phenomenon is only seen in monopolar because it is a unidirectional current and this entire loop has to be completed. And it is so designed in a way that only at the entry point thermal energy is generated and not at the exit point. So main application of monopolar in laparoscopic surgery is usually for cutting. It's used for cutting the vault. And if you see that there is a pinpoint cutting which can happen, but it can also be used for coagulation when you have to spray coagulate over a wide area. Like for example, there is a venous plexus or there is a wide papillary plexus which is happening and which you are not able to pinpoint and coagulate with your bipolar. Then a monopolar is very helpful here because of its characteristics. So if you jump to the third last line, if you see that the lateral thermal spread when you use monopolar current at any tissue is almost 2 to 3 centimeters. So this itself proves the point that if you want to coagulate a widespread area, then monopolar is a very good energy source. But the negative being that because of this lateral spread of 2 to 3 centimeters, if you use this monopolar near the vital structures, then there can be lateral thermal spread. So what you have to be very careful about is that when you cut the vault, you are cutting it at the level of the cardinal ligament, where the attachment of cardinal ligament is, or just below that. And at this point, the ureter is narrowest, ureter is the closest to the cervical area. So if you're not careful in this area, or if you have not adequately dissected your bladder down till the vagina, or if you have now adequately cut and dissected the uterosacral and the cardinal ligament wide enough, what will happen is that due to this 2 to 3 centimeter phenomenon of lateral spread, the current can cause your thermal damage at the ureter at this point. And this is solely the point where we usually use a monopolar. And if you have seen, I've written cutting is safer because if you go into deep physics of monopolar, it is basically works on the principle of sine waves. And in coagulation, what happens is that there is high wavelength sine waves for a short period of time. And then, no, actually I got it wrong. There is, in cutting, what happens is there is sine wave for some period of time. After that, it flattens out and it again repeat. But in coagulation, what happens is you have continuous sine waves throughout the time you are going to activate the machine. So just understand that if you have to choice between using the coagulation mode and cutting mode is much safer. Many people make this mistake of using the coagulation mode to cut the vault also. Even if you use cutting or coagulation mode, the tissue will get cut. There is no doubt about it, but it is going to come at a higher cost, higher lateral spread, higher thermal damage. And there is a phenomenon in monopolar when there is high amount of resistance, there is a chance of current jumping to various sites. For example, if you've got the bladder close to the area where you're activating the monopolar, due to the high resistance, the current can jump to the adjacent tissue. It can be either the bladder, it can be the bowel. So this makes monopolar very dangerous if not properly used. And sometimes what happens is there might be leak or aberrations in the monopolar hook, which also causes decreased resistance and again jumping of current. So whenever you're using monopolar, be very careful that there are no vital structures nearby. For example, no bladder, no ureter, at least within 2 to 3 centimeters, no bowel nearby. If you're very cautious about all these things, then there won't be damage. But if you're not, if you're a very new person using all these monopolar energy sources, be very careful because current can jump and current can also travel, thermal damage can also travel up to 3 centimeters. But all said and done, this is one of the most economical energy source we have in our tray. So next is the basic bipolar. Bipolar is one of the most common energy sources used by gynecologists. Before going to bipolar, if you really want to see how a monopolar is used judiciously, then you should see surgeons doing cholecystectomy. So once the gallbladder is removed, there is sometimes widespread oozing from the liver base. So they use this monopolar to fulgurate the liver surface for a wide area so as to stop that oozing. Bipolar won't work there because it's not pinpoint coagulation which is happening there. It's a diffuse plexus bleeding which is happening. They run the monopolar over it for a long period of time in order to cause the superficial coagulation. So in comparison to the monopolar, bipolar is actually a bidirectional current. So the very simple fact that there is no patient plate required while you are using the bipolar. Patient plate is only required for monopolar. In this, current travels from the machine to the handpiece. The current is transmitted between the two jaws of the handpiece, and then through the cord it again goes back to the machine. So in this, the patient is not part of the circuit. And here, if you notice that monopolar hooks are always a single, there is no jaw shaped or there is no forceps kind of attachment seen in it. But bipolar will always be a forceps. There will be two jaws. Monopolar will only have one jaw because it only has to have a unidirectional flow of current. In bipolar, the current flow happens between the two jaws of the instrument, from one jaw to the another, where tissue stays in between, causes the resistance, and this causes it to heat up and cause coagulation. So, as I said earlier, monopolar is more effective for cutting, but bipolar is the most effective for coagulation. But there are certain modifications of bipolar also. If you have seen, bipolar sharers have come, which because of the modification of jaws, they have made the jaws quite sharp that it can do coagulation and cutting based on the way you're using it and also based on the pressure you're applying for the tissue. So if you apply too much pressure, the cutting happens sooner. If you don't apply too much pressure, then coagulation happens, and then you can progressively increase the pressure to cause the cutting. But the main function of bipolar is always and always for coagulation. So as the lateral thermal spread is only 1 to 1.5 centimeters, it is much safer than monopolar. So this is the very reason, if you have seen my videos on TLH, when I come to the uterosacral ligament, I always make sure that uterosacral ligament is cut and dissected laterally, because cutting the uterosacral properly and lateralizing it gives us an additional 1 to 1.5 centimeter lateralization of the ureter. So whenever you are using even monopolar or bipolar at the vault level, giving this 1 to 1.5 centimeter lateralization of ureter protects it. So many people, what they do is after cutting the uterine, they directly go on to cutting the vault because vault will be easily visible there. Just by putting a vaginal tube, the vault can be delineated. But make sure that you cut the cardinal ligament and also the uterosacral and lateralize it so that the ureter gets lateralized at least 1 to 1.5 centimeters, and this safeguards the ureter. But if you use a bipolar cautery on a tissue for a long period of time, what happens is there is a phenomenon called charring which happens. So I'll explain charring, why it happens, because when you apply bipolar, if you can see this diagram, I've put few diagrams here. If you notice the diagram down without the numbering. So when the bipolar starts activating, are you able to see my cursor? Is the cursor visible, the mouse cursor?
Yes, sir.
Okay. So if you see this figure, when bipolar energy is applied to the tissue, what happens is the coagulation starts happening at the outsides first. So when this outside area gets coagulated first, what happens is again resistance increases because water is the only one which has resistance in the tissue. So when this gets coagulated or denatured, first resistance increases on the external surface. And then it is a struggle for current to enter inside. So when you keep on cauterizing at one point, even after the bubbles are seen or even if the tissue is cauterized, what happens is there is a lot of charring happening. So in short, what happens is when you coagulate any tissue or when you fire any tissue, always the external aspect of it gets coagulated much more than the internal aspect. So once it gets coagulated, the tissue resistance increases far more, and then the current or the tissue the heat does not reach the core, and you may go to proceed and cut the tissue, but what happens is that the core is going to be still not coagulated. So you may feel the uterine artery is completely coagulated, seeing charring on the surfaces, and when you cut it, the tissue, the vessel starts bleeding. So in these cases, what you have to do is that even though you have seen charring, pour some water on it. You can either use a irrigation cannula and pour some water on it to hydrate the tissue. And when you start firing again, what you'll see that you'll see fresh bubbles appearing on the tissue again getting cooked. So this will confirm that your vessels have been totally cooked or sealed before you're cutting. And if you see this diagram number 4, this is the perfect way of applying a bipolar forceps to any tissue, especially a vessel. It has to be perpendicular. It should not be extended too much, because if you extend too much, what happens is that the tip of the bipolar is also active. The tissue, the electrical energy or the current gets transmitted to the other tissues also, which are beyond the vessel or beyond the tissue of target. And what will happen also is that the bipolar forceps cannot be closed fully if the tissue comes very close to the joint. So keep it at a mid level, don't extend it too much, and make sure that you are perpendicular to the vessel to cause maximum effective sealing. These are all wrong methods. If you have seen the one, what happens is it is tangential, so that the distance between the jaw increases and the coagulation won't happen properly. Two, as I mentioned, the vessel is going to be very close to the joint, the closure won't happen and the coagulation won't happen. And third one, what will happen is there will be partial coagulation, only a pinpoint coagulation of the vessel. The other part of the vessel will be completely unsealed and open. So always use perpendicular for the best result and use it at the mid level. So this is in short about the bipolar energy source. Now heading on to the advanced bipolar. So what is the difference between bipolar and advanced bipolar? So the basic, if you have heard, there are certain instruments called ligashore, thunderbeat. Thunderbeat is not very popular now. N-seal. These are instruments which are glorified but are just nothing different than bipolar, but they're just advanced bipolar. So the key is this, the second one. In advanced bipolar, there is a tissue feedback mechanism. So when you activate the instrument and try to coagulate a tissue, the tissue actively senses the resistance and gives feedback to the machine. And when the resistance has increased or reached a maximum level, the feedback indicates a signal to the machine that the tissue has been entirely cooked or coagulated, and a beep sound comes and automatically the current gets cut off. This is the only principle of advanced bipolar. That is why it's called advanced compared to the normal bipolar. So this tissue feedback mechanism ensures that the current flow does not happen beyond a certain limit. The tissue gets coagulated. After that, automatic current cutoff or supply cutoff happens. The tissue charring is minimal, and it also ensures that sealing happens. So this advanced bipolar is definitely safer than the normal bipolar in many ways. The lateral thermal spread is also lesser. It's only up to 0.5 to 1 centimeter, and you're not going to do much charring of the tissue, and there is not going to be much spread of current. But the only problem is that it's time consuming, because they entirely depend on the tissue, the machine to sense that the tissue has sealed and to cut off the supply. And one more advantage is that the same instruments can be used for coagulation and cutting also. It happens in two phases. Once you coagulate, completely wait for the coagulation to happen. There is a beep which happens with signal which says it has been cut off. And using another switch on the side, you can cut the tissue in the same step. So cutting and coagulation can be done. Primarily it's for coagulation, but added advantage of cutting is also there. Only disadvantage is it comes at a higher cost compared to the normal bipolar, and most of these instruments have an instrument count. For example, ligashore can be only used for 5-6 cases. N-seal also same 5 to 6 cases. So they all have a tissue or instrument count is there while you are using these instruments, compared to a normal bipolar where you can keep on using it even for 100-200 case, depending on how you're maintaining it and using it. And coming to the last energy source of the day, which is considered to be the most advanced as of now, is the ultrasonic energy. Ultrasonic energy, what you have to understand is that it is also similar to the bipolar, but what happens is there is a machine which has electrical energy, and in the interface you have got a transducer, which is usually called the handpiece. These transducers have crystals in them which converts the electrical energy to sound energy in the machine. Sound energy basically means vibrations here. So the transducer converts the electrical energy to the sound, which is in ultrasonic range. Why is it in ultrasonic range? Because the induction of this sound energy causes the tip of the instrument to vibrate at 55,000 hertz per second. It's a very high value. So what happens in this is that any ultrasonic energy has got two blades, just like a normal bipolar. There are two parts of the two jaws, two blades are there. One is going to be the active blade, one is going to be the passive blade. This passive blade is just going to support the tissue. And just like the bipolar, as I had shown in the earlier picture, for example, if you see this figure, one is going to be active blade, one is going to be passive blade. Just imagine this is an ultrasonic scalpel. So this blade, passive blade, just supports the tissue, and this blade does a frequency of 55,000 hertz per second. So what is essentially doing is that this blade is rubbing this tissue against this blade. This rubbing or this friction is what is going to cause the thermal energy or heat to be generated. And this heat evaporates the water, the causes the proteins to denature and coagulation to happen. So this is the simple principle of ultrasonic energy. Electrical energy getting converted into sound energy, which is frequency of vibration. This high frequency vibration causes friction, which is going to cause the tissue to coagulate and get sealed. So based on the pressure you apply for these blades, you can either do a coagulation of the tissue or cutting of the tissue. So both coagulation and cutting are possible in this. And it is the safest because lateral thermal spread is just 3 to 5 millimeter. That is 0.3 to 0.5 centimeter. Compared to, see, in monopolar, we had 2 to 3 centimeters. We came down to 1 to 1.5 centimeter for bipolar, and this is just 0.3 to 0.5 centimeters. But again, the disadvantage being there is going to be a high recurring cost because all these instruments, transducers, instruments all have a particular case count. It depends on how you use it and how you utilize them case to case. Just as a summary, what I've spoken so far, we have spoken on monopolar, bipolar, advanced bipolar, and ultrasonic energy. First three are electrical energy directly applying, causing heat due to resistance, and ultrasonic is a sound-based energy. Monopolar primarily is used for cutting, can be used for coagulation also. So when you come to bipolar, advanced bipolar, and it's more of coagulation and cutting. Lateral monopolar is 2 to 3 centimeters, bipolar 1 to 1.5, advanced is up to 1, and ultrasonic is 0.3 to 0.5 centimeters. Safety profile from monopolar to ultrasonic is least to maximum. When the safety profile is least, the most economical cost is very less. But as the safety factor, as all the other features go up, the cost is also going to go up. So this one slide, if you want to save, anyways, I'll upload the recording also. This one slide will serve as the summary of what I've spoken today. It will also help you practically choose and apply these instruments. Finally, no perfect energy source. It all depends on you want to use, how you want to use, based on your resource setting, which case you're doing. It's not the energy source which decides, it's always the hand which operates it. That's what I say as a benchmark. A lot of people ask me, what is your favorite energy source? What is the favorite instrument used? Whatever be the instrument, finally, how you use it, how you plan to use it, what decides how you're going to do a case. And always read the pros and cons before choosing which instrument you I hope I have covered most of the aspects of it. And if you want to ask anything regarding this, please feel free. If you have not understood anything, also please feel free to ask. I'll clarify. Was the concept understood or not at all understood? Is there anything I need to clarify? Even if you have a question, you can put it in the chat box also. I'll be more than happy to answer. No questions means either nothing has been understood or everything has been understood. I'm hoping it's the latter. Okay. So I'm hoping there are no questions. So we'll wind up the session. Thank you all for joining.
Thank you, Akshay.
Thank you, ma'am. Thank you.